Imagine a high-speed data path receiving millions of bits per second. Somewhere in that massive stream, a specific overlapping binary sequence is hiding, and your hardware needs to catch it the exact microsecond it occurs. Our objective is to design a cycle-accurate pattern detector for the sequence 1011. The most common trap for junior ASIC and FPGA engineers is approaching this problem like a software developer. They sit down at their workstation and attempt to write Verilog as if it were a sequential C program. But processors read software line by line, moving sequentially from one instruction to the next. Hardware description languages do not execute code. They define physical structures that operate simultaneously. You can see the divergence here. The software loops through operations in distinct steps. The hardware evaluates every gate instantaneously on every clock edge. Because of this parallel reality, we cannot trap temporal sequences using simple software variables. We have to construct physical state memory to hold a historical record of what the circuit has already seen. To build this properly, we have to move past the legacy ambiguities of Verilog 1995. We will architect our detector using modern SystemVerilog semantics, which enforce rigid structural rules. And to guarantee its accuracy, we will replace standard procedural test benches with SystemVerilog assertions, embedding formal mathematical checks directly into the design. Abandoning the software mindset in favor of a syzypal temporal framework is the requirement for creating synthesizable, production-ready silicon. Before we write any RTL, we need a mathematical blueprint. We must map the abstract progression of time into discrete, trackable physical states. We do this using a finite state machine. At the structural level, a robust FSM requires three distinct hardware blocks: a state register to hold the current memory, next state logic to determine the path forward, and output logic to signal a successful detection. Let's map our specific pattern. We start in an idle state. When a 1 arrives on the data line, the machine transitions to state S1. The hardware effectively remembers the first valid 1 in our target sequence. As new inputs arrive on subsequent clock cycles, the sequence builds. A 0 drives us to S10. Another 1 pushes us to S101. Now we must address the overlapping requirement. If we receive the final 1, we have successfully detected 1011. But that final 1 simultaneously acts as the first one of a potential new sequence. So instead of returning to idle, the machine loops directly back to S1. With the state transitions mapped, we have to choose our exact architecture type, a Moore machine or a Mealy machine. For an overlapping pattern detector, the Mealy machine offers a distinct advantage. Its output evaluates based on both the current state and the current input, rather than the current state alone. This grants us lower latency, asserting a detection on the exact cycle the pattern completes. This abstract node diagram is not hardware yet. It is the rigid mathematical logic required to prevent chaotic signal routing before we begin coding. Now we transition from the theoretical blueprint to the explicit physical structures of our register transfer level code. Legacy Verilog relied on generic always blocks, leaving the synthesis tool to guess the designer's intent. SystemVerilog eliminates that ambiguity with strict specialized semantic keywords. We map the state memory using the always FF block. This is the physical anchor of our design, where we define how the current state register updates to the next state value only on the positive edge of the clock. This keyword strictly instructs the synthesizer to stamp out sequential edge-triggered memory components, like D flip-flops, and ensures the synchronous reset is routed safely. Next state and output logic blocks are mapped using always COM. Here, we translate every arrow in our FSM diagram into conditional case statements, defining exactly how the current state and the incoming data bits interact to drive the next transition. In Legacy Verilog, if you missed an else condition or omitted a default case in a combinational block, the tool would quietly infer a latch to hold the state. Unintentional latches destroy timing paths and ruin silicon yields. The always COM block acts as a strict semantic enforcer. If your logic inadvertently implies memory within a combinational path, the compiler immediately throws an error, halting the build before a mistake becomes physical. We can verify the power of these semantics by looking at the actual synthesized result generated by the tool. This is a synthesized gate-level schematic. Look at the yellow logic block on the left, labeled state. Because we used always FF, The synthesizer explicitly instantiated a dedicated sequential register driven by the clock and reset inputs. Moving outward, you can trace the paths from those state registers directly into the pure combinational logic, the OR gates and inverters that evaluate our always-calm conditions to drive the final output. Utilizing strict SystemVerilog semantics forces the synthesizer to perfectly match the structural intent, ensuring the design behaves exactly as the RTL specifies. Even with perfect synthesis, standard procedural test benches are inherently flawed. They only stimulate the exact edge cases the engineer remembers to write code for. To achieve true verification closure, we introduce SystemVerilog assertions. SVA allows us to encode formal mathematical rules and temporal constraints directly into the hardware description. This waveform shows the temporal requirement of our detector. We need to verify that over 4 consecutive clock cycles, the data line transitions precisely through 1, 0, 1, and 1. We map our assertion code directly over this physical timeline. The double #1 syntax is a temporal delay operator. It explicitly forces the verification tool to evaluate the condition on the very next consecutive positive clock edge. This formalizes time. The assertion fires an unignorable failure if the sequence breaks at any point, and asserts a pass only upon precise, cycle-by-cycle perfection. Formal verification tools can use these assertions to search for any possible violation, providing a level of confidence in the design's temporal integrity that standard simulation alone cannot reach. With the state space mapped, the semantics enforced, and the timing formalized, we initiate the final synthesis. The entire engineering pipeline is visible. We move from abstract state machines through rigid code structures, bounded by rigorous temporal checks. The ultimate goal is condensing this logic into a physical blueprint, a gate-level netlist optimized for area, power, and speed. Remember, hardware description languages are not code. They are maps of a spatial reality. This is the final manifestation: microscopic parallel logic pathways executing thousands of operations concurrently on a silicon wafer. Mastering this pipeline, from behavioral FSM modeling to explicit structural semantics to formal temporal verification, is the hallmark of a senior ASIC designer. True hardware engineering requires letting go of the sequential software illusion and mastering the simultaneous physical reality of logic synthesis.